So our next speaker is Professor Christian Ruff. Christian is in the Department of Economics at the University of Zurich, and he's conducted groundbreaking work on human motivation, on decision-making and learning. He's going to present work on magnitude representations in parietal cortex, I think, and with the aim of understanding how and why risk preferences can change across different task contexts. Christian.
Yeah, good morning from my side. Thanks to Jason and Dragan for putting together this symposium and giving me a reason to come here to this beautiful country and city. I'm very glad that I'm here at this great conference. I want to tell you today about our research on the neural processes that determine your risk attitude, how you deal with uncertainty in your life. I think you all know these situations. There are options that are okay, not particularly exciting, but at least you know what's going to happen. Think a career in city administration, for example. And then there's the things you really like, you know, the options that are exciting, but it's not quite so sure whether they're going to materialize. Our career choice, science, for example. So what should you do? These choices are so prevalent in all aspects of our life that pretty much all, this doesn't work. I cannot advance. Can someone tell me why? I'm pressing the big green, yeah. Yeah, giving the talk without slides is not really an option, I think. Okay. These situations are so prevalent in our lives that pretty much all languages have come up with advice for how you should decide. And if you look at this, it becomes clear that there's no right or wrong answer in these situations. Some people say you should play it safe. Others say, well, if you don't dare, you really don't gain anything. So that's what we mean by risk attitude. You have to take your own balance here. You have to find your own balance. Economists have been interested in risk attitudes for a very long time. So now the mouse is also not working. And this is not working. Okay. Bit complicated. Economists have been interested in this for a long time because risk attitudes determine behavior in many economically relevant aspects of behavior. So how do we study risk attitudes? We have people play lotteries like this for real money, right? You choose, do you want $14 for sure, or $28 with 55% probability, or zero not, right? And you're called risk neutral if you choose by expected value. So if you just multiply probability with amount, and then choose based on that. If you have to be paid more to accept the uncertain gamble, then you're risk averse. If you have to be paid less than what you need for the expected value, you're called risk seeking. Now, if you run these studies, then you see that there's lots of individual variability. Many people are risk averse, but many others are risk seeking. First question, why is that the case? Why do some people shy away from risks? What you also see is that there's huge context variability. So depending on how you frame these questions, or if you stress people, if you put them under time pressure, these risk attitudes can change, and people can become risk-seeking in some contexts and risk-averse in others. And again, the question, where does that come from? So that's why we run our research program, in which we try to identify the neural processes that causally determine our risk attitude, because we can think it can help us with answering all these questions that we have. So where could it come from? Well, if we look to classical economics, we can go down all the way to Bernoulli and say it could be subjective valuation. So people don't decide by the objective numbers on the screen, but they subjectively like, uncertainty, or they don't like it. So it's all got to do with affective evaluations. And that's why in neuroscience, people have focused a lot on subjective value systems, say VMPFC or ventral striatum. And there's also research that has shown that the insula, for example, responds to uncertainty. So there's been a strong focus over several decades in neuroscience now on these affective brain systems. But the question that I always had is, well, so where does that come from then? Yeah, so it correlates with the value that you assign, but why does your brain assign higher or lower value to uncertainty? And there's not many studies that have really answered that. So like Dragan here, we decided to basically go down to other parts of the brain and say, well, perhaps it has something to do with the way we see the world. So going back all the way to Helmholtz, there's this a strong theoretical tradition that our brain has to infer based on the noisy signals it gets about the environment what the most likely state of the world is. So equipped with beliefs and expectations, the brain basically then computes, infers the most likely interpretation of the world. And this can be extremely pervasive, as you can see in all these illusions, for example. You can't see two rings that don't touch here. You actually see a spiral, right? So we thought, well, given that in many of these situations you have to perceive numbers and probabilities, is there something about the probabilities of these numbers, some biases that we have that are inbuilt, so to say, that would lead to us underestimating large numbers and therefore appearing risk-averse, for example? And of course, if we run psychophysical experiments like this, so if we present people different magnitudes, there are lots of models, Bayesian models, that we can then fit, and we can determine both how sensitive people are, but also how precise their representations mentally of that are. Neurally as well, we can use population receptive field mapping. This is a bit like retinotopic mapping, but now for magnitudes. And that's because in our brains we have populations of neurons that are sensitive to magnitudes. So they're tuned to particular magnitudes, and they have Gaussian tuning. And together, if we fit these population receptive field models, we can determine for every voxel of the brain which magnitude they're most sensitive to. And that reveals maps like these that I'm showing on the right. And we're mainly interested in those in parietal cortex, intraparietal cortex, because that's where they're most prevalent and strongest. So equipped with these tools, psychometric tools that allow us to measure the precision of mental magnitude representations, and neural mapping techniques that allow us to estimate the precision of neural magnitude representations, we now went in and asked the questions, do individual differences in risk attitudes perhaps reflect individual differences in magnitude precision? So the way that we did it is we put people in a scanner and we had them do a purely perceptual magnitude task. So we show them two magnitude dot clouds, these are franc coins, and we measure the neural response in presentation to the first of these two. So there's no decision. People are just looking at it and asking themselves, how many franc coins are there? And we can derive a measure of neural precision there. And then, when they see the second, they have to decide which of the two contains more. And by fitting now models to the behavior, we can also get a measure of perceptual magnitude precision. And afterwards, outside the scanner, different context, we have people take risky choices, either based on the very same stimuli or just with symbolic numbers, because we want to see whether it generalizes across contexts. And our aim is to now predict the risk aversion in this separate behavioral context from our measures of perceptual and neural magnitude precision. So how do we get this neural magnitude precision? It's an imaging conference, so I'm quickly going to tell you about it. We basically fit a population receptive field model, which you see on the left. So the assumption is that each voxel contains a mixture of the different neurons that have tuning for the different magnitudes. And this model has 4 parameters: the baseline activity, then how strongly that voxel, how strongly the response profile actually is, and how wide it is, and then also some baseline activity. So we just fit this model to the data for every single voxel, and then we get estimates of the preferred numerosity and the corresponding maps. And now in the second step, to infer the precision of these representations, we now go to unseen data that were not used for model fitting, and we invert the model. So we basically just say, given the fitted model, what's the probability that this population of neurons actually saw any given stimulus? So what we get by doing this for every voxel and summing this up is now not a tuning function, but a PDF, a probability density function, a posterior, that tells you the probability that this population saw this particular stimulus. And this gives us 2 things. This first gives us the most likely stimulus. And if you now look here at the matrices on the bottom right, you will see that we can decode really well with that what particular stimulus people saw, right? So the highest values are on the diagonal, and if anything, on the off diagonals, it's very close. So we can decode well. But the second thing, and that's very interesting for us, is now the width of this posterior on any given trial. So that tells us how precisely the population actually encoded that particular representation. So if we now take all these measures, the measure of neural precision, perceptual precision, and risk aversion, and put them in a joint model, then we find evidence that indeed, if I know the neural precision just from looking at the response to a magnitude stimulus in a perceptual task, I can already predict how risk-averse someone will be outside the scanner. And this is mainly mediated by the perceptual precision that people have actually in terms of their mental representations. So the second question we wanted to address with this was now these context effects. So how can it be, if we have this, that in some contexts we're more or less risk averse? So we're thinking, if it is really the precision of these representations that determines this, then we should introduce noise with particular context in these representations. And the way that we did it is we now had people in the scanner again, but now they actually performed the risky decision-making task. And we showed them one set of choice problems, but we repeated it and we showed them in different orders. So in one instantiation, they saw the risky option first. In the other, they saw the risky option second. Sorry, it's a, yeah. Mm-hmm. So what does that do? Well, it's known from working memory research that if you hold the stimulus in working memory, the representation is a lot noisier than if you see it on the screen. Okay, so it means very same choice problem, we can now make either introduce noise in the representation of the risky option or in the representation of the safe option. Okay, and the basic logic is that this should lead to stronger perceptual bias in line with Bayesian inference, so stronger over or underestimation, and therefore change risk attitudes if these actually rely on these perceptual representations. Yeah, I don't have time for this, I guess. So this is now also what we see. So we did this twice, once in 3T and once in 7T. The dots are the data, and the lines are the model, the fitted model. So a model fits the data very well. And what you can see is indeed, if the safe option is presented first, so the risky is presented second, and it's more precise, so less bias, you will see that people are actually more risk-seeking. Yeah, so they don't underestimate the risky option so much. That's what you see in the left plots. The blue curve is higher than the red curve. What's even more interesting, I think, is the plot on the right of both of these panels. Here you see what happens when the risky option is first and is noisy. So now the biases should be stronger, and this is exactly what you see. So you see that for small risky options, they're overestimated, people actually become risk-seeking, whereas for large risky options, it's underestimated, and people actually become risk-averse. And as I said, we replicated it twice, and our model can fit it, and none of the existing subjective value-based risk models in the literature can explain this pattern. So it's uniquely explained by this perceptual account. Now, we were also interested actually now in neural fluctuations. So we again decoded the magnitudes from the first stimulus, and our reasoning was, and I think at this conference I don't need to tell you, the brain shows ongoing fluctuations, right? There's periods where your brain is more precise and periods where it's less precise, arousal fluctuations. So we thought, what if we now look at periods where your brain is very precise, periods where it's not so precise, and look at risk attitudes then? So what we did is we divided trials into those. We're just looking at the neural representation of the first stimulus, nothing to do with choice, first stimulus, where our decoder says this, the representations are very precise, or where they're not so precise, and then looked at the behavioral choice biases for these two trials. And this showed that on trials with high neural precision, people were indeed less biased, so less risk-seeking for small offers and risk-averse for large offers, whereas on trials with low neural precision, so where the imaging tells us this is when your brain doesn't represent magnitude so precisely, these biases become exacerbated. Yeah? So people are more risk-seeking for small and more risk-averse for large offers. Crucially, I want to point out, this is not something that you see at the average level. If you just look over all trials, it's not that risk attitudes per se change. It really is this context-specific effects. And that's what I find quite interesting, because the literature is quite confused about how different contexts change risk attitudes. And finally, we regressed now the behavioral biases on these neural effects. So we incorporated in our model a parameter that actually allowed the strength of the behavioral bias to co-vary with the trial-to-trial neural uncertainty measure. And that parameter was significant, really indicating that there's a strong, tight correspondence between these behavioral and these neural effects. So I think I'm way over time. So one more minute, okay. So just quickly, the question is this causal? So is there just a third factor, something like arousal? Or can we say that these parietal regions really are causally responsible for choices? So we ran a TMS study. We invited people, derived for them the individual magnitude fields, selected people where we could stimulate them very well, and then gave them a standard CTBS protocol over the individual parietal magnitude field. And in the second session, we gave them vertex stimulation, counterbalanced order. And what you can see is that the parietal simulation indeed leads to more noise, so lower decoding accuracy. So our assumption that it actually changes noise was validated. And then I can't go in detail over it, but it is causal. So risk attitudes change with stimulation, showing quite clearly that there are, this is not just an epiphenomenon. People really rely on these representations for their choice. So a couple of closing words. I hope to have shown you that our risk attitudes that we see in behavior don't just reflect what we like or don't like about risk. They reflect, at least in parts, the precision with which we perceive magnitudes. And this is important for theories of risky decision-making economics. It's important for attempts to try to optimize behavior, allow people to deal better with uncertainty. And of course, for anyone doing brain imaging, don't just look at VMPFC and look at, you should look at the sensory system. I think you can learn a lot from that about risk-taking. Just very quickly, perhaps the last bit, I just want to emphasize again these context effects. I'm quite excited about that because in the field we've really puzzled for a long time why changing the light in the room or time pressure or something changes risk attitudes around, and not really just in one direction but varying directions. And I really think it is these psychometric models that really specify clearly how your expectations interact with the actual context, that could actually do something. And I really don't want to stop without thanking the people who actually did all this work. So Gilles de Hollander, mainly, Maris Moisa, who helped with the TMS study, who is here in the room with us, all the other collaborators, my lab, and the funders. Thank you very much.